Good morning. I hope you guys are all doing well. This video is about, we're in chapter 7 now, it's about polar coordinates. So this is the introduction to polar coordinates, and we're going to be learning what this coordinate system is. It's an alternative to the rectangular coordinate system, which is what we've been using probably most of our math life, what you guys have mostly been exposed to. But polar coordinates are a very nice and convenient way to express a point in space, particularly when you're interested in how far something is from a certain point. For instance, if you have a city where a storm is coming, you want to know how far the city is from the storm, maybe. Or if you have airplanes coming in to land, you want to know where they are, like an air control tower and airplanes. You want to know where they are. So this is what the polar coordinate strength is when you are interested in knowing how far something is from a point in space. So we're going to look at that. So here is what we've traditionally known is the rectangular coordinate system. So that is the XY axis. It's also called the Cartesian coordinate system. All of those mean the same thing. So here's our traditional coordinate system here with our Y-axis here and our X-axis here. So if we have a point in space, here, let's just pick a point here, X, Y. It has two coordinates that would describe this point. It's a two-dimensional graphing space, so it needs two coordinates to describe it. And so whatever this number is, so we'll just make up some numbers that would suit this. Let's just say this would be maybe -3, +3, and -4. Okay. These 2 points describe this point in space in the rectangular coordinate system. What is different about the polar coordinate system is that there's not one way, as there is in the rectangular coordinate system, to describe a point, but there are an infinite number of ways you could describe a single point. So for instance, just for ease, I'm going to move this point from quadrant 4 to quadrant 1 just because it's easier to think about. So let's just move this up here. Let's call this the point maybe 3, 4. Let's move it up here just so we can discuss what the difference in the two systems are. So let's just say this is the point 3, 4. What if we want to describe that in the polar coordinate system? What the polar coordinate system is, it has an origin just like the rectangular coordinate system. So in the red, I'm going to draw a polar coordinate system. It starts with a pole right here at the origin. And so then it has an initial axis, which typically the initial axis will be the horizontal x-axis right here. This would be the initial axis. So you think about, if this is the pole, how many degrees would it take to rotate from this initial axis all the way up to this? So we would think about from the pole to here. So how we describe this point in the polar coordinate system would be with this angle theta, how far do we have to rotate to get up to there, and this length, the length of this vector r. So we would say this point in the polar coordinate system would be described as the length of this sort of ray and the angle that it took to rotate up there. And so as with our same convention, when you are moving counterclockwise, the angle's positive. When you're moving clockwise, it's negative. And so we can describe this angle in radians or degrees as a positive angle or a negative angle. And for that reason, we could describe this point in space many, many different ways. So let's take a specific one that we know about. Let's see, that's the big difference between the two systems. Let's just take this point in space. Let's pick something off the unit circle here that we're familiar with. So right now, let's talk about this point in space, and let's say that this is, instead of we'll convert the 3, 4 over here in a minute. So let me just hang on to that point that I chose. We'll convert that in a minute. But for now, let's just learn about this system. Let's say that we had this point in space and that this angle theta was maybe at 45-degree angle. So let's say that the length of this ray is 6. So r goes there. And then how far up has this been rotated? We'll say 45 degrees. So all I'm doing is I want to illustrate all the different ways we could talk about this. So just as a visual, here's my unit circle, here's 45 degrees, and we'll say that this is 45 degrees. Okay, what's another way we could describe this point in space? What's another way we could describe this point in space? Well, we could, instead of calling it 45 degrees, we could talk about it in radians. Okay, here's one way. We could say we could also describe this point in space as 6 pi over 4. All right. We could also say, well, what if we didn't want a positive angle, but we wanted a negative angle? So we could say, okay, instead of moving this way, let's move this way around the unit circle. And so this point in space would be, let's see, that's pi, negative pi, and that's negative 3 pi over 4. This would be negative 7 pi over 4. So this would be, we could also call it, say, 6 negative 7 pi over 4, because that's the same place on the unit circle as pi over 4. What if we wanted to call that out in degrees? Okay, we could say this is 6. Let's see, what is 360 minus 45? Oh, it'd be negative 315 degrees. That's another way we could call this out. Okay, here is something else you can do with polar coordinates. You could talk about the angle 180 degrees opposite that. And then if you still wanted this point over here, 6, you would call it negative. So here's another way we could talk about this same point in space. Okay, opposite 45 degrees, right, is over here. What is that? That's negative 90. Okay, this is negative 135 degrees. Okay, what we could do is say, let's find this angle, which is 180. Okay, so this angle right here, opposite 45, could be called out as 225 degrees, or it could also be talked about as negative 135 degrees, or it could also be talked about as, this is as 5 pi over 4, or it could also be talked about as negative 3 pi over 4. That would get us to this point on the circle. So how could I talk about this positive 6, this same point? You can describe this same point like this, or you could say, let's go to the point 180 degrees off. So let's go to this angle, 225 degrees. Let's go all the way here, but instead of going this direction with a positive number, let's go negative 6. And so what you would do is you go all the way to here, and then you would go the opposite direction if this is negative, up 6. Here's another way we could describe this. Negative 135 degrees would be here. Let's describe the same point in space. So if we said negative 135, once we go to here, if I have a negative 6, we're going to go the opposite from this direction, which is up here. That still describes that same point. You could do it in radians. We could say negative 6, 5 pi over 4, negative 6, negative 3 pi over 4. All of these describe that same point in space. So that's the big difference in the polar coordinate system and the rectangular coordinate system. So this looks like there's only 8 ways to describe it, but if you think about coterminal angles, all I got to do is add 360 to this, and I'm hitting that same angle again. So we could do that infinitely many times. That's why there's so many ways to describe it. Okay, now the big thing I want to talk about is how to convert between rectangular and coordinate system and polar and vice versa. So over here, let's look at just a point in space right here. This is the rectangular coordinate system. How do they relate? How can we convert these? If we look at this point P, which got an XY coordinate, let's draw the the polar part to this. So what if this was, this from here to here is how far that is. So if we think about this point in space, and we draw like a vertical down there, from here to here, this distance right here is x. This is how far it took to get to this point. And then from here to here is y. Okay. And we know that r, if we're thinking about polar coordinates, this is the length of that ray is r, and the angle it took to get there is theta. All right, how do all of these relate? Well, we know a lot about trig at this point. And so let's just say this is a right triangle, so we are allowed to use the trig functions that we've learned. If I was interested in knowing x right here, is there a trig function that I could involve with x and theta? And if I want to involve this adjacent side, cosine comes to mind. This is one I could use. So let's talk about that. Let's say the cosine of the angle theta is equal to adjacent x over hypotenuse r. So if I solve for x by multiplying both sides by r, I get that x is equal to r times the cosine of theta. What if I was interested in knowing y right there? Okay, y is opposite, so sine involves opposite over hypotenuse. So I could say that the sine of theta is opposite over hypotenuse, and I could multiply both sides by r and get that the r sine of theta is y. These are conversion properties. If I know r and theta and I want to solve for y, these are the formulas I will use. So let me just write that up here. These are important ones. X is equal to r times the sine of theta, and y is equal to r, I'm sorry, got that wrong. X is r cosine theta. And again, this is not that hard because all through the course, we've been associating cosine with x and sine with y. Y is equal to r times the sine of theta. Okay, that is how we can get back and forth if we know if we're given r and theta and we want to find x and y. What if we are given x and y and we want to find r? Well, let's go back to see how these relate. The tangent of theta is equal to opposite over adjacent. So that would be y over x. We could take the inverse tangent right here, and then we could find theta. So theta is equal to the tangent inverse of y over x. So if we're given x and y and we need to know theta, theta is equal to the tangent inverse of y over x. What about r? What if we need to calculate the length of r? Well, this is a right triangle, and for a long time now, you guys have known about the Pythagorean theorem, and so let's do that. A squared plus b squared equals c squared. X squared plus y squared is equal to r squared. If I want to solve for r, I'll just take the square root of both sides, and so we find that r is the square root of x squared plus y squared. So r is the square root of x squared plus y squared. This is how I would convert to polar if I was given x and y coordinates, rectangular. This is how I would convert to rectangular if I'm given polar coordinates, r, theta. So now we're going to practice. So let me erase most of this stuff. I'm going to leave the purple things on here. And this point that I first just put up on the board to make sure we know how to do that. So you guys have some problems you can do on your worksheet. I have picked some that just to get us started, and maybe one that might be harder for you guys. So let's just say we were given these polar coordinates, and so I happen to write these out in radians. Of course, you could also use degrees. Okay. So okay. If we have to convert, so our job here is to convert from polar to rectangular. So what I'm going to do here is know that x is equal to r cosine theta. So for A, x is going to be equal to r, which is 5. See, this is r and this is theta. 5 times the cosine of pi over 6. And y is going to equal to r, 5, times the sine of 5 pi over 6. All right, I don't know where I got 5 pi over 6. Pi over 6, sorry. All right, so if this is what we're given, r theta, we just do this direct conversion. So I would expect you to give me exact answers to this. And so right here, we would say, oh, here is our unit circle. And so where is pi over 6? Pi over 6 is right here. What are the coordinates? What are the xy values of pi over 6, the cosine and the sine? Well, right here, it's square root of 3 over 2 and 1/2. The cosine of pi over 6 is the x value, square root of 3 over 2. So we would say this is equal to 5 times the square root of 3 over 2. Or 5 square root of 3 over 2. Right here, y, what would it equal to? 5 times the sine of pi over 6, which is 1/2. So y would be 5 over 2. The rectangular coordinates for 5 pi over 6 would be 5 square root of 3 over 2 and 5/2. We've just converted from polar to rectangular. Now, let me do one with a negative in it. -4, -7 pi over 6. So I'm going to skip down here to C, because I don't want the video to be too long. So I'm just going to do a couple of these examples, and you guys do all of them on your worksheet. And then we can talk about any questions that you have in the Zoom meetings that we'll be having. So, all right, so C, -4, -7 pi over 6. -4, -7 pi over 6. If we have to convert to rectangular, we know that x is equal to r cosine of theta. So this would be -4 times the cosine of -7 pi over 6. We just write it down like that. Y would equal to r, -4, times the sine of -7 pi over 6. Well, where is -7 pi over 6? Well, this is negative, meaning we're going to go clockwise. So this is -pi, and -7 pi over 6 would be right here. This is -7 pi over 6. So what are the sine and cosine of this angle? Well, really this is, if we think in positive terms, 5 pi over 6. So the x coordinate here is negative square root of 3 over 2 and positive 1/2. Okay, so x is equal to -4 times the cosine of -7 pi over 6, which we figured out that the cosine is negative square root of 3 over 2. And y is equal to r, which is -4, times the sine of -7 pi over 6, which is 1/2. So when I multiply these together, I find that the x coordinate is -4 times negative square root of 3 over 2. Let's see, 2 can go into 4 twice. A negative times a negative is a positive, so we get 2 square root of 3. 4 can go into 2 can go into 4 twice, -2. Those are the rectangular coordinates for, I didn't do B, for this one, for -4, -7 pi over 6. Now, if we have to go backwards, if we're given x and y and we want to convert to polar, let's pick this point in space that I chose 3, 4, okay? Let's do that one, and then we'll do one that's not in quadrant 1. This is what we would do. I'm going to erase all this stuff now. And so, let's see here. What if, let me erase this stuff here. What if we are given this point, 3, 4, and we have to convert. So we have to convert to polar. And so right here, let's say we're given the point 3, 4. So we know that this is x and this is y. Well, we know that r is equal to the square root of x squared plus y squared. So we're just going to straight calculate that. This is going to be the square root of 3 squared plus 4 squared. This is equal to, let's see, square root of 25. So this is just the number 5. R is equal to 5. How about theta? How do we find theta? This is the tangent inverse. Theta is equal to the tangent inverse of y over x, or 4 over 3. Now, I will need my calculator for this, and so if I want it in degrees or radians, that we got to figure out whatever I asked you to do. Let's do degrees. So let's see. Second tangent inverse of 4 divided by 3. We get 53.1 degrees is what I get there. All right. So if we said r theta. So that would be a way we could describe the 0.34 in space. Okay, now on your worksheet, let me do one of those and then we'll be finished with all this. Let's do, what if they say convert? This is what it says on your worksheet. So we'll be, this will be something you'll have to be able to do when I ask for not using your calculator or to give me exact answers. So what if I give you this? Let's do B on this page because it's not in quadrant 1. So let's see. What if they say convert to polar and they give us negative square root of 3, negative 1. All right, this is our X and this is our Y value. We can calculate R by just saying this is what this is. R is equal to the square root of X squared plus Y squared. So this is the square root of negative square root of 3 squared plus negative 1 squared, okay? This is the negative times negative is positive, square root of 3 times the square root of 3 is just 3. Negative 1 times negative 1 is 1. This is the square root of 4, this is 2. R is 2. All right, we got that much. Now we have to figure out theta. All right, ready? Theta is equal to the tangent inverse of y over x of negative 1 over negative the square root of 3, which is positive 1 over the square root of 3. That's true. But here is where we've always had to be very careful about what quadrant we're in, and we still have to be careful about that here. Do you see this x and this y, negative, negative? That means we're in quadrant 3 right here. So you have to think about in your unit circle, right? On your unit circle, in quadrant 3, who has a sign of, whenever I have a tangent, I have to, when I think of my unit circle, I always put the over 2's because these are numbers I recognize. Who has a sign of negative 1/2 and a cosine of square root of 3 over 2? Or in quadrant 3, we're looking for a big X and a small y. A big X and a small y, or negative square root of 3 over 2, negative 1/2. Sine over cosine would be 1 over square root of 3. Let's see. That is going to be 7 pi over 6 is what this angle is when I look at my unit circle. So theta is 7 pi over 6. So we have to be careful that we choose the angle that would be in the correct quadrant. That's the only little tricky part right there. If you have questions about this, bring them to the Zoom meeting or email me and we'll try to make sure all of your questions get answered. But that's basically how you convert.